All right, thank you for watching this video. I hope everyone's having a nice spring break. Today we're going to talk about Chapter 19, Solubility and Complex Ion Equilibria. And so this is going to give us two new equilibria to deal with. KSP, which is the solubility product equilibrium, and KF. KF, it's not written here, but that's section 19.8. It's formation of complex ions. That's what KF stands for. And so we're going to be looking at these. And we're going to try to manipulate the solubility of different solids by primarily by using Le Chatelier's principle, the common ion effect. That is, normally when we think of the common ion effect, we think of it limiting the amount of forward reaction, but there are ways that we can decrease the amount of common ion as well as increase the amount of common ion. And the ways we can decrease or increase is just by physically adding it or by using chemical reactions or physical properties to decrease or increase the common ion effect. But let's go ahead and get started here with what is the solubility product here. And so that's the KSP equation. KSP equation just broadly is, was supposed to be a K, but let me try that again. KSP. This is just the solid and saturated solution equilibrium. Why is this so equilibrium here? Okay, I just did a quick change to Word because something with my tablet is making writing difficult. But anyway, this is the solid to saturated solution equilibrium. So if we have a beaker and I put in some solid, and this is going to be the equilibrium that describes the dissolution, that is the dissolving of the solid, and the precipitation. And that is, what happens is these particles in the solid solution, can collide with the crystals here and recrystallize or precipitate. And so when we have a saturated solution, what that means is that the dissolution rate, that is the dissolving of the crystals, is equal to the crystallization or the precipitation rate. If we have an unsaturated solution, then what happens is that in an unsaturated solution, the dissolution rate is going to be greater. So I can have some solid here, and the net dissolution rate will be faster than the precipitation rate. And what needs to happen is we need to build up the concentration, because the higher the concentration, solute particles that are in solution, the greater the crystallization rate. And so the more particles we have that are dissolved, the more they're going to impact on the surface of the solid here, and when they impact on the surface there, they can get stuck. And if they get stuck, we call it precipitation. Okay, so once that occurs, then the solution's saturated. So it's unsaturated here, and eventually over time it'll become saturated. Once it becomes saturated, then there's no more net dissolution. So over here we have net dissolution that occurs. And saturated, then the two rates are equal. So we have chemical exchange, that is, the crystals never stop dissolving, but they're precipitating at the same rate. So there's no net change, but this is dynamic equilibrium. So crystallization and precipitation continue. It just goes in circles here. Okay, when we have a saturated solution, then what tells us what a saturated solution is? A saturated solution, is one we've maxed out. solubility. And so solubility has two ways that we define it. One way of defining solubility is qualitative. When we're looking at qualitative solubility, we just have some cutoff. The cutoff is going to be a gray area. So for example, if the solubility, which I'm going to use the symbol S for solubility, if the solubility is less than 0.1 molar, then we call it insoluble. And then sometimes we use an I for that. If the solubility is greater than 0.1 molar, then we say it's soluble. And so there's going to be some overlap with these terms. We give an S, which is a different S than this. If the solubility is about 0.1 molar, then we call it slightly soluble. And we use the term SS. And so this is qualitative solubilities. These qualitative solubilities we use for solubility rules. You know, that's one of the major applications of this. You know, is it fairly soluble? Is it fairly insoluble? Or is it slightly soluble? Then we have a quantitative definition of solubility. Quantitative. And in the quantitative, when we're talking about solubility, solubility is the max amount that will dissolve in a given amount of solvent. And so max amount that will dissolve. In a given amount of solvent. You know, the typical units for this are grams per 100 milliliters of, let's do this, see what happens. Okay, there you go. So an example would be, you know, sodium chloride. Sodium chloride is what we consider soluble, S, but there is a limit to how much you can dissolve, and that limit is about 36 grams per 100 milliliters of water. So as long as we're under 36 grams, then it should completely dissolve in 100 milliliters. But if we go over 36 grams, then any extra will not dissolve, and the solution is considered saturated with sodium chloride. But it's still quite a lot, so we give an S, you know, versus other things like silver chloride. When we look at silver chloride, it has a very low solubility. You can only get a very limited amount of silver chloride in solution. And so sodium chloride, this is what we call highly soluble, but these aren't the most soluble. Highly soluble. There are things that are even more soluble than that. You know, if we take it to the limit, you know, there are things that we call miscible. Miscible substances are like infinitely soluble. That is, there's no limit to how much you can dissolve. And sodium chloride is not miscible in water. Usually, when we think about miscible, they're like the same phase. All right, so we're looking at this equilibrium, and what we're going to do is we're going to look at different solids. And typically what we do is we look at KSP for insoluble solids. Because KSP is used for insoluble solids. Um, so, for example, for sodium chloride, we really wouldn't use the KSP topic. So KSP is used for insoluble solids, that is, the ones that are less than about zero point 0.1 molar, not soluble solids like sodium chloride, even though it's not miscible. Because we're talking about high concentrations. As we get to higher and higher concentrations, then our calculations are going to be less and less accurate due to deviations from ideal behavior. And so when we're thinking about KSP, we're thinking primarily of insoluble solids here. And so let's take a look at some KSP equations and KSP values. So an insoluble solid would be something like silver chloride. You know, chlorides are all soluble except for silver, lead, and mercury. So if we look at silver chloride, then the KSP equation for this is the solid is going to be in equilibrium with its saturated solution. Saturated solutions contain silver ions and chloride ions. And this is our KSP equation here. And the KSP equation is just going to equal the silver ion concentration at equilibrium times the chloride ion concentration at equilibrium divided by the activity of silver chloride. Activity of silver chloride is 1. And so it's just the product of the soluble species ions here. This is the KSP. And so what we can do is we can measure how much of this dissolves. And this would be molar. So there are other units. You know, typical units would be something like grams per 100 milliliters. It's supposed to be 100 milliliters down there. Or molarity, or whatever other concentration unit you want to use for this. You know, grams per 100 milliliters is pretty visual, versus molarity, it's a little less visual as far as, you know, what is the molarity of this? You know, and so this is less than, I don't know, what is the molarity of that? We'd have to figure it out. Is it there? That would be 360 grams per liter, 360 grams per liter, and the molar mass of sodium chloride is 23 plus 35, which would be about 58 or so grams. And so less than 10 moles. But anyway, these we can relate to solubility. It turns out that when we do the ice table here, okay, silver chloride is a solid, so we're just going to ignore that, and then we're going to look at this. So initially we're going to assume that nothing has dissolved, and then what we're going to do is we're going to let this dissolve, the silver chloride, and it's going to dissolve, and it's going to end up saturating the solution. So at equilibrium we have X molar and X molar here. It turns out that this X is the maximum concentration that we're going to get. And so what we're going to do is we're going to say that the maximum amount of silver chloride that dissolves is going to equal the silver ion concentration, which is going to equal the chloride ion concentration in this case, which is going to equal X. So silver chloride that dissolves, so this is going to be the formula units that dissolves. And then whatever else doesn't dissolve stays as solid. So how much dissolves? Well, it's a 1 to 1 to 1 mole ratio, so that gives us our X there. And what we're going to do is, since that's the maximum amount that dissolves, that's also called the solubility. And so we'll just call this the solubility. And then what we're going to do is we're going to use the symbol S for this. And so instead of calling this X like we would normally do, we're going to get rid of the X here and then just call it S plus S. We're going to get rid of that X, S. And so at equilibrium we're going to have S and S. And so what this is going to mean is this is going to equal S times S, which is just going to be S squared. And so it turns out that the solubility for this is just equal to the square root of the KSP. KSP here. So we can do two things. We can either measure the solubility and determine the KSP, or we can look up the KSP and then determine the solubility. Well, it turns out looking up the KSP is not difficult. We can find that in a table here. Let's take a look at the table, KSP values here. We can find these in Appendix D, and we can also find a table in Chapter 19, which is a little shortened table. But one of the things that you should note here is that when we're looking at the KSP values, they're all quite small here. And aluminum hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. So aluminum hydroxide is considered an insoluble hydroxide. And the KSP value is quite small, 10 to the minus 33. Phosphates are all insoluble except for group 1 and ammonium, 10 to the minus 19. Carbonates are insoluble except for group 1 and ammonium, 10 to the minus 9. Chromates are insoluble except for group 1 and ammonium, 10 to the minus 10. Chlorides, bromides, and iodides are soluble. However, fluorides have a lot more exceptions, so it's more difficult to incorporate those into a general rule. And so instead for fluorides, we look them up. So something like barium fluoride, which is group 2 fluoride, is insoluble. And the fluorides are going to be a lot less soluble because fluoride is a smaller ion than chlorides, bromides, and iodides. And being a smaller ion, it's going to form stronger ionic bonds. And so we have barium fluoride, which is fairly insoluble. And so looking at all these, let's take a look at the smallest KSP value, which is 10 to the minus 33 so far. And then we'll look at the largest. Lithium. Now, you know, these rules, there's always exceptions to rules we got to worry about. It's not a law. So something like lithium carbonate, lithium is a group 1, but it's on the small side. And so we're going to see more exceptions with the smaller ions like lithium, which is a group 1 cation. And fluoride, you know, those are smaller, and so they're going to have stronger electrostatic attractions with the opposing ion, which forms stronger bonds, making it less soluble. And so there are a lot of exceptions for lithium shown here. So for example, lithium carbonate, 10 to the minus 2, lithium fluoride, 10 to the minus 3, lithium phosphate, 10 to the minus 9, so all fairly insoluble, or the lower end of the solubility spectrum. So that's an exception. Here we have magnesium ammonium phosphate. This is mixed cation. So magnesium's +2, ammonium's +1, and phosphate's a -3. And magnesium ammonium phosphate is actually quite insoluble here. The solubility 10 to the minus 13. So we haven't done too many mixed cation or mixed anion salts. Carbonates, you know, that follows our rule. Fluorides are a bit more of an exception. So magnesium fluoride is quite insoluble, but magnesium hydroxide is quite insoluble, but calcium, strontium, barium hydroxides are much more soluble. So those we have. And so these are lots of carbonates. Sulfides are typically insoluble except for group 1, group 2, and ammonium. And so sulfides are quite insoluble here. And so far the smallest we've seen is 10 to the minus 33. The largest so far is 10 to the minus 2. However, there's even smaller ones here than that. Like, for example, sulfides I mentioned are quite insoluble. Mercury 2 sulfides, 10 to the minus 53, which is very insoluble. There are patterns here that you can look at for the carbonates and whatever, but we're just going to look up the values in the table, not necessarily worry about all the patterns here, but you know, they are typical ones that we worry about. Sulfates here, like calcium sulfate. Sulfates are typically soluble, except for silver, lead, mercury, etc. Calcium, strontium, barium. So calcium sulfate appears here. So minus 53 so far is the smallest we've seen. Let's see if there's any larger or smaller. Minus 51. Looks like that could be it there, minus 53, which is a sulfide. So the sulfide was the least soluble, and the most soluble is this lithium salt, which is a 10 to minus 2, which is the lithium fluoride, I think it was. Oops, went too far there. Or no, lithium carbonate, which was it. So the smaller the KSP value, the lower the solubility, but it's a little bit more complicated because it depends also on how the ions split. So for example, for silver chloride, the solubility was equal to the square root of the KSP value. Here's the KSP value. But for other salts, insoluble solids, we see that the way it splits up is different. Like for silver chloride, we get 1 silver and 1 chloride, but for something like silver carbonate, we would get 2 silvers and 1 carbonate. And that changes the relationship between the solubility and the KSP. So it depends on how the solid ionizes, how the solubility is related. So sometimes you can be tricked into something having a smaller KSP, but because of how it ionizes, it might actually end up being more soluble, not less soluble than something with a bigger KSP value. But anyway, let's go ahead and calculate some solubilities here. So we'll take a look at silver chloride and figure out what the KSP value is. So from the table, and then we'll use that KSP value to determine what the solubility is. And so let me go ahead and just take this value here. 1.8 times 10 to the minus 10. Let's throw that here. This is the KSP. And we just determined that, let me get this, that the solubility is equal to the square root of that from the ice table above. And so we'll just take 1.8 times 10 minus 10 square root. And what does that give us here? 1.8 times 10 to the minus 10 and square root 1.34. Okay, what's going on? 1.341 times 10 to the minus 5. The units here would be molar. We could plug this back in to do a check. We can check that if we square this, will it give us back our KSP? Yes, it gives us back our KSP. So that would be our check to plug the equilibrium concentrations back in. Okay, 1.341 times 10 to the minus 5 molar, which is like how many grams per liter. It's how many grams per liter. Let's take a look at the molar mass of silver chloride, which I'll just look up here rather than calculate it. $143.32. So we'll go back here, and then just figure out how many moles of that we have in a liter. All right, so we have the solubility in terms of molarity, and then we're also going to get the solubility in terms of grams per, not per milliliter of water, but grams per liter of solution. So let's go ahead and do that. It was 143.32 grams per mole. And then go ahead and calculate it, what it's going to come out to. Let's see, my pencil's stuck here. There. Okay, times 143.32 grams per mole. And so what's that going to give us? So if I take what I had, oops, I guess it cleared. 1.341 times 10 to the minus 5 times 143.32. This gives us, come on, there we go, 0. Let me change the thickness of this. 0.0192. Stuck again. 0.00192 grams per liter, which is going to be 1.92 milligrams per liter, or about 1.9 milligrams per liter. So it's not 100% insoluble. Even though we say silver chloride's insoluble, it's not 100%. 1.9 milligrams of silver chloride will dissolve in a liter. But that's below the cutoff. The cutoff is 0.1 molar. This is 0.00001 molar. And so it's well below our solubility cutoff. So we can have things even more soluble than this. In fact, one thing that is more soluble than this is, for example, lead-2 chloride. And so this will be the next example we'll look at, calculating the solubility. And so if we look at lead-2 chloride, that has a fairly high KSP value. And so let's take a look at the KSP value here. The lead-2 chloride is 10 to the minus 5, which is about 6 orders of magnitude higher. It's not on the highest end. On the highest end were these lithium salts, but let's go ahead with lead-2 chloride because we call that insoluble as well. 1.6 times 10 to the minus 5 is its KSP value here. And so this is the data we get from the table. KSP is 1.6 times 10 to the minus 5, which should be considerably less soluble. But one thing about lead-2 chloride is it ionizes differently than silver chloride. And so the first thing is we'll need the KSP equation. The KSP equation is a solid in equilibrium with its saturated solution. Its saturated solution consists of lead ions and 2 chloride ions here. And then we'll just go ahead and generate an ice table for this. What we do is reset everything so that nothing's dissolved, and then let it completely dissolve. And so for every mole of lead-2 chloride that dissolves, we form 1 mole of lead. So that's plus S here. But we form twice as much chloride, and so this is going to be twice as much chloride, which is 2S. And so we end up with S molar and 2S molar at equilibrium. And then the KSP value here is going to equal the lead concentration, lead ion concentration times the chloride ion concentration squared. And so this is going to give us S times 2S quantity squared, which is going to give us 4S cubed. And so we get a different relationship between solubility and KSP. In this case, the solubility is going to equal the KSP divided by 4, and we'll take the cube root of that to the 1/3. And so we'll just plug in our KSP value here, which was 1.6 times 10 to the minus 5. So 1.6 times 10 to the minus 5 and then divided by 4 equals, and then I'll take the cube root of that. So, oops, syntax error. Try that one more time. Okay, let's see if that works. Yeah, and so here I have a solubility of 0.01587. This is stuck here again. Let's get this out of there. 0.01587 molar. So that's the maximum. This is below 0.1 molar, so this is classified as insoluble. And then let's go ahead and get the molar mass to see how many grams of lead-2 chloride dissolve per liter over here. It should come up around here. Wikipedia has solubilities listed here. Solubility, or molar mass. Actually, what I wanted was a molar mass. Where did it go? 278.10. 278.10. So times 278.1. gives me 4.414 grams per liter. So that's considerably more. Close to 4.5 grams of lead-2 chloride will dissolve in a liter. That makes it a saturated solution, and so we get a lot more lead versus silver in solution. So even though this has much higher solubility, it's still classified as insoluble because of the molarity, here. All right, that's another example. And so there are other examples as well of how things split. For example, if it splits into 3 ions, we get a different relationship. So an example might be something like sodium, or actually not sodium phosphate, lithium phosphate. Lithium phosphate. Sodium soluble, so we don't really do KSP calculations with these. Lithium phosphate, however, was classified as insoluble here. So we can take a look at lithium phosphate as far as the KSP value. 3.2 times 10 to the minus 9. It's quite a bit less soluble. But the reason I'm bringing up lithium phosphate is this is going to have a different splitting pattern. And so when we look at lithium phosphate solid is going to be in equilibrium with its saturated solution, which is going to consist of 3 lithium pluses, oops, it should just be plus a phosphate here. And so we set up the ice table again, and we end up with resetting this so that nothing has dissolved. And this is going to be plus 3s here. This is going to be plus s. So we're going to get 3s molar lithium ions and s molar phosphate. And so the solubility of lithium phosphate, that is, for every mole of lithium phosphate that dissolves, we form 1 mole of phosphate. And so it's a 1-to-1 ratio between lithium phosphate and phosphate. And so that's the S relationship here. But what happens is we split up into 3 lithiums, which is triple the solubility of this. So that's triple S here. But essentially what it's going to boil down to is that the KSP is going to equal, in this case, the lithium is going to be cubed here, and the phosphate here. And so this is going to be a 3s cubed S situation. And so 3 cubed is 27, so this is going to be 27s to the 4th. And therefore the solubility is going to equal the KSP divided by 27, and then we'll take the 4th root. Oh, not that. And so the relationship is different there. And we can do the calculation. The calculation would be very similar to what we've done so far. All right, so that's the KSP and solubility relationship, the KSP equation, the KSP expression. All right, the next thing we're going to look at will be the common ion effect here. And so relationship between solubility and KSP, common ion effect, and solubility equilibria. And so we call this precipitation in the laboratory when we do this. And so we add a precipitating agent. The precipitating agent would be the common ion. So for example, if I wanted to precipitate out silver ion, I just add chloride. And we could add chloride in different forms like HCl or whatnot. And so that would be qualitatively. And so let's look at the common ion effect. In fact, we're going to be looking a lot at the common ion effect. And solubility. And so here, I mean, the lowest was going to be 0, if we have 0 common ion. And so that's what we call solubility in water. And so everything that we've calculated so far is a solubility in just pure water, nothing else. But what we're interested in is we're interested in the solubility in other types of solutions. So, for example, when we were doing the precipitation of silver chloride in step 1 of our qualitative analysis, we were adding HCl. And so we had silver ions in there. And then we were adding HCl to this. And then what we're trying to get is a precipitate of AgCl here, with H plus as being a spectator out over here. And so essentially this is what we're doing there. Now, this is from the qualitative analysis, step, what was it, 2? Something like that. And so for us, when we want to understand this, we want to understand, is it possible to precipitate all the silver ion? The only way we're going to precipitate all the silver ion is if we add an infinite amount of HCl, which is not possible. So when we're doing these precipitates and precipitations, I kept mentioning about complete precipitation. Now, complete, for me, does not mean 100%. Otherwise, you'd have to add an infinite amount of HCl, which is not possible. And so complete, we have a different definition of complete we talk about. And complete usually just means this. Okay, unfortunately, the second part of my Camtasia recording failed. And I did all the notes and I went through the whole lecture, but what I'm going to do is I'm just going to go back through, but not rewrite everything. And so we had left off talking about the common ion effect here and the solubility and precipitation. And so in our qualitative analysis lab, we did this precipitating out the silver ions using hydrochloric acid. This forms silver chloride, and the H plus is a spectator in this case. In order to precipitate out the silver ion, we increase the HCl. So we increase the HCl, the amount of silver ion decreases, and we increase the amount of silver chloride precipitated. And we could do that by adding Z. So for example, we could add 0.1 molar, or we could add whatever. We could just keep adding more and more chloride. And so I just called it Z molar chloride. And this is the common ion effect. And so essentially what we do is, even though this is a precipitation reaction, we visualize this in terms of this dissolution in the forward and precipitation in the reverse, the KSP equation. And so we set this initial. Now this is going to be a common ion type problem where we do have some Z in here to begin with. And the Z is whatever amount, that we put in there. Let me go ahead and highlight that here. And so that means the solubility S is going to be smaller than in pure water. And so in pure water, we'll have a higher solubility because we're starting off at 0 and 0. But now we have Z in there. The equilibrium is going to consist of S and Z plus S. So the more Z we have in there, the lower the solubility is. And that means if we're starting off with some silver, that means it's going to be less soluble. That is, we'll get more precipitate. We could kind of visualize it using a chart here. This is the silver ion concentration, the free silver ion concentration. And on the x-axis, we have Z molar, HCl, ZHCl. So if we have 0, we get the maximum amount of silver that dissolves, that is the highest solubility. However, as we increase the amount of common ion, the solubility decreases, and we're going to get less and less silver in solution. And so this is what we see is this decreasing trend. For complete precipitation, we would want to get 100% of the silver out. That is, we want the silver ion concentration to go to 0. But when we look at this chart here, the silver ion concentration doesn't go to 0 until the chloride concentration hits infinity. Well, that's going to be impossible. We can't have an infinite amount of chloride in there. It's physically not possible. And therefore, what's going to constitute this complete precipitation? And so what we do is we redefine what complete precipitation is here. Complete precipitation, this is an arbitrary definition, is 99.9% precipitation. And so that means we need to get 99.9% of this curve here, and then we'll just stop there. That means there's going to be 0.1% residual silver ions or remaining silver ions that are unprecipitated. And so that's going to be close enough. Now, this is arbitrary. It's not 99.99 or 99.95, something like that. This is 99.9%, an arbitrary set point here. But what that does is it leaves a minimum amount of residual, and that's going to be complete. To be truly complete is not feasible because of this infinite amount that's required here. All right, and so we can try a common ion / precipitation type problem in this example here. This example is we're going to take about 10 drops of 0.100 molar silver ion solution, or about half a milliliter. Half a milliliter is about 10 drops. And then to that, we're going to add 3 drops of 6 molar HCl. it should be about 0.15 milliliters. So whenever we combine two solutions, 0.15 milliliter of the hydrochloric acid solution with half a milliliter of the silver ion solution, then we have to do step I solution dilution. So the final volume is going to be 0.65 milliliters, the combined volume here, 0.50 plus 0.15. And then we have solution dilutions that we have to do. So chloride, which is going to be the same thing as HCl here, the H plus is a spectator, so I'll just ignore it. The chloride initial after solution dilution will be a 15 part to 50, not 50, but 65, 15 to 65 dilution of 6 molar. That gives us 1.38 molar. And the silver ion is going to be a 50 to 65 dilution. 50 to 65 dilution, 0.100 molar, which gives us 0.0769 molar. Now, what we want to do is we want to figure out, will we get a precipitate? That is, is this going to shift to the left? What's going to happen here? So we can do a Q test. In the Q test, we look at Q. If it's less than K, it's unsaturated. If it's unsaturated, we're going to get no precipitation because we have plenty of space in solution for those. If Q is equal to K, it's saturated. And so if it's saturated, nothing's going to happen until we go supersaturated. Supersaturated is a condition where we have Q greater than K. And when Q is greater than K, we're going to get precipitation. Now, we don't always have to do this Q test or not Q, Q analysis, whatever you want to call it. We can just go ahead and assume it precipitates and then figure out what we're going to get. But in this case, I'm going to go ahead and do it. I'm going to calculate QSP, which are the initial values that are given here, and see how that matches with KSP. So when I calculate the QSP, I get 0.106, which is a heck of a lot greater than the KSP. The KSP is 1.8 times 10 minus 10. And therefore, this is supersaturated and will precipitate. Now, the next question is, yes, it precipitates, but how much will it precipitate? Will it completely precipitate or incompletely precipitate? And so we set this up as an ice table here. That's what I did here. Again, the KSP equation, whether it's precipitation or dissolution, I use the same KSP equation. I don't flip it because I don't want to invert this or do whatever. And so I start off with the initial. The initial silver ion, what we had was 0.0769. The initial chloride ion was 1.38. This is after solution dilution. Now, the K value is very small, 10 to the minus 10, so I'm going to reset this to the left. So I'm going to precipitate out 100% of the silver and bring that to 0. And that's going to consume that amount of chloride. So I'm going to lose all my silver and this amount of the chloride. That's going to leave me with 1.303 molar chloride left over here. Okay, now once I reset the initial conditions, I'm going to go ahead and approach the equilibrium from the left here. So I get plus S molar, and then I'm going to have over here S molar and 1.303 plus S molar. And now I want to solve for S. And so KSP is going to equal S times 1.303 plus S quantity. And I'm going to use a simplifying assumption here. This is going to equal S times 1.303, and then S is going to equal 1.38 times 10 minus 10, which gives us about 10 to the minus 8%. So that checks out. So the SA is valid. We can do a K check. So I'm going to calculate the equilibrium concentration. So the equilibrium concentration of silver is this, and the equilibrium concentration of chloride is this, and that K checks out. 1.798 times 10 minus 10, it should be 1.8 times 10 minus 10, which is good. Okay, now what we have to do is we have to figure out how much precipitated. In order to figure out how much precipitated, we have to calculate how much remains. And so we have 1.38 times 10 minus 10 molar silver ions remaining out of initial. The initial wasn't 0 because that was our reset initial. The initial was 0.0769. So we started off with 0.0769 and we only have 1.38 times 10 minus 10 remaining. So calculate the percent remaining as 1.38 times 10 minus 10 divided by 0.0769, our initial, times 100%. This gives me 1.79 times 10 minus 7% remaining. Okay, in order to determine the percent precipitation, we take 100% minus this. So whatever doesn't remain was precipitated, and that comes out to 99.999998%. which is greater than 99.9%, so we call this a complete precipitation. And so with 3 drops, it completely precipitated. We could do the calculation with 2 drops and see if we get complete precipitation, or 1 drop and see, if we get complete precipitation. So this is an example of that, common ion type precipitation. Another example of a common ion type precipitation problem is fractional precipitation. In fractional precipitation, we had our mix of cations. This is from qualitative analysis. We had a mix of 2 plus and 3 plus cations. And what we want to do is we want to see, okay, what happens. As we add hydroxide, do all 7 ions precipitate at the same time with a slow addition of hydroxide? It turns out no. Which ions precipitate first? The least soluble one will precipitate first. So out of these, which one is the least soluble? And so to figure out the least soluble, we can go back to the KSP tables and compare the ions here. And so we had iron, or actually, iron, let's do aluminum. We'll do aluminum first because aluminum hydroxide is 10 to the minus 33. And then iron 3 hydroxide, just scroll down here, iron 2, iron 3 hydroxide, 10 to the minus 38. So that's so far the least soluble. And then chromium, 3 hydroxide, was 10 to the minus 31. So out of those 3, it's going to be the iron. Iron is going to be the least soluble, so that should precipitate first. However, we need to compare that with the 2 plus cations. The 2 plus cations were calcium, magnesium, nickel, and zinc. But it's not a fair comparison because the 3 plus cations split up into 4. So aluminum hydroxide splits up into 4 ions, 1 aluminum, 3 hydroxides. However, if we look at calcium hydroxide here, that splits up into 3, 1 calcium, 2 hydroxides. Since it splits up differently, what that does is it makes it not as straightforward. In fact, when we're comparing these, it's not fair. We should compare ones that split up the same with others that split up the same. However, if we're comparing one that splits up into 4 ions and another that splits up into 3, it's best to calculate the solubility. But before we do that, what I want to do is I want to figure out which of the 2 plus cations is the least soluble. Calcium, magnesium, nickel, and zinc. So let's go to calcium hydroxide and take a look. Calcium hydroxide is 10 to the minus 6. And then we're going to go to magnesium hydroxide. Magnesium hydroxide is 10 to the minus 11. So magnesium hydroxide is less soluble. And then we're going to go to nickel hydroxide, nickel 2 hydroxide, 10 to the minus 15. So that's the least soluble so far, nickel 2 hydroxide. And then we go to zinc hydroxide. Zinc hydroxide is 10 to the minus 17. So zinc hydroxide is the least soluble. So the least soluble 3 plus cation is iron 3. The least soluble 2 plus is zinc hydroxide. So let's just compare those two rather than compare all of them. And so here, I'm going to calculate the solubility of iron 3 hydroxide. Iron 3 hydroxide here splits up into 4 ones. And we can relate the solubility to the KSP here. And so I set up the ice table, assuming nothing's dissolved, and then we're going to get plus S iron, plus 3S hydroxide. And then this is S here. 3S for the hydroxide means it's 3S quantity cubed. 3 cubed is 27. And then S is going to be to the 4th, 27S to the 4th. So that means the solubility is equal to the KSP divided by 27, and we'll take the 4th root of that, which gives us a solubility of 1.96 times 10 to the minus 10 molar. Okay, zinc hydroxide was the least soluble 2 plus. But you can see it splits up differently. 1 zinc, 2 hydroxides. That's going to give me an S and 2S here. And so this is going to be S, 2S quantity squared, which is 4S cubed here. And therefore the solubility is KSP divided by 4 to the cube root, which gives us this. 10 to the minus 6 molar. So 10 to the minus 10 molar versus 10 to the minus 6 molar, 10 to the minus 10 molar is less soluble. So out of all the cations, iron 3 will precipitate out first. What do I do here? Chromium? No, iron. And so the question is, can iron 3 plus be separated completely from zinc 2 plus? That's supposed to be an iron 3 plus, not a chromium. Let me fix that here. So this is, can iron 3 plus be separated completely? Now, what we need is concentrations here, because the concentrations will impact this. We plug in the concentrations up here as well. And the higher the concentration, of these, the less soluble things become. And so we're going to keep it simple. We're going to keep the concentration the same. But we have to take it on a case-by-case scenario, because if iron 3 plus is 0.100 and zinc is 0.200, then that could change the dynamics. Because if we have a lot more zinc than iron, then maybe the zinc precipitates first. And so it can be an unfair comparison in that sense. Or maybe the zinc is 6 molar. In that case, for sure, the zinc might precipitate first. We'd calculate it, though, just to make sure. Okay, so the strategy here is we want to maximize the precipitation of iron 3 plus. Again, I made a mistake here. Let me fix that here. Okay. This one. Pen. Oh no. Alright, so my Camtasia crashed. Now my Word is about to crash. But I think I'll still be okay, because I don't really need to write it. So we want to maximize the precipitation of iron 3 plus, stopping right at the point where zinc 2 plus will begin to precipitate. In other words, we want to stop at the point where the QSP for zinc hydroxide is equal to the KSP of zinc hydroxide. That's called saturated. We don't want to go beyond saturated, because that would become supersaturated. And so the calculation that we do for fractional precipitation is we determine the hydroxide at which each ion will precipitate. And so first I calculate the hydroxide required for iron 3 hydroxide precipitation. And that's going to just be rearranging the KSP equation, solving for hydroxide. We get the hydroxide of 7.368 times 10 to the minus 13. And with this hydroxide, we'll have a QSP equal to KSP. If the hydroxide concentration is greater than this 7.368 times 10 to the minus 13, we're going to get precipitation, because it's going to result in a QSP greater than KSP, which is supersaturated. However, if the hydroxide concentration were less than 7.368 times 10 to the minus 13, it's an unsaturated solution, and we get no precipitation. Now, that's the point at which it will begin once we exceed that hydroxide. For zinc, the hydroxide requirement is rearranging the KSP equation is 4.932 times 10 to the minus 6. And so for zinc to precipitate, we need a heck of a lot more hydroxide. Rather than 10 to the minus 13 molar, we need 10 to the minus 6 molar, quite a bit more hydroxide. If the hydroxide is greater than this amount, we get precipitation. If it's less, it's unsaturated. And so we need to stop when the hydroxide hits this amount. That is, we want to exceed the amount for iron. That means iron precipitates, but we want to stop once the zinc becomes saturated and not go beyond that. And so what that means is we're kind of doing like a titration where we have 0.100 molar iron 3, 0.100 molar zinc, and we do a slow addition of hydroxide, thereby increasing the hydroxide. Okay. Once we hit a hydroxide concentration of 7.368 times 10 to the minus 13 molar, then iron will begin to precipitate. So we continue increasing the hydroxide, and the iron 3 hydroxide precipitates here. And then we continue to increase the hydroxide. As we continue to increase the hydroxide, the iron 3 concentration decreases. So continue to increase the hydroxide, iron 3, it says iron 2, but it's supposed to be iron 3,
decreases, resulting in higher precipitation or more precipitate forming. However, we can't just keep going up and up and up in hydroxide. We have to stop here. When the hydroxide hits 4.932 times 10 minus 6 molar, we need to stop. If we exceed that amount of hydroxide, then both ions precipitate. We don't want both ions to precipitate. This is what we're trying to do here is we're trying to do a separation, a complete separation. Okay, and so how much iron 3 plus remains at our stopping point? And so that's our next calculation. The iron 3 plus remaining is equal to KSP divided by the hydroxide. The hydroxide maxes out at 4.932 times 10 minus 6, and we know what the KSP value is, and that gives us an iron 3 plus remaining of 3.334 times 10 minus 22 molar. So the percent that remains is 3.334 times 10 minus 22 molar at the end, at the stopping point, versus 0.100 at the beginning. And that gives me 3.33 times 10 minus 19% of the iron remains. And the rest is precipitated. So that would be 100 minus that, which gives us 99.9999, etc. percent. Well, this is well beyond 99.9%, and we call this a complete separation. So what we can do is, as long as the hydroxide doesn't get too high, in other words, as long as the pH doesn't climb too high, we can separate the +3 cations from the +2 cations effectively, that is, completely. And so that's what we did. The way we made sure the hydroxide doesn't get too high in our qualitative analysis is by making the buffer. It was ammonia buffer, and that prevented it from going up. Well, anyway, that is it for this. There, that will actually that took remaining. And so we'll continue from here next week after spring break. All right, thanks for watching, and I'll see you Monday.